you to picture something for a second. Take every galaxy you've ever seen in a photograph, every spiral arm, every cluster, every faint smudge of light captured by Hubble or Webb, and understand that all of it, every single galaxy we know about, sits inside a structure so vast that the galaxies themselves are basically grains of sand stuck to a spider's web. That web is real. Cosmologists call it the cosmic web, an enormous scaffolding of dark matter and gas that threads the entire observable universe together. Galaxies don't float randomly through space. They line up along filaments, these long, thread-like bridges of matter that stretch tens of millions of light years and funnel gas, dust, and momentum from one end of the cosmos to the other. Now here's what I find genuinely unsettling about a paper published in December 2025. A team at the University of Oxford, using South Africa's MeerKAT radio telescope, found a filament 140 million light years from Earth that appears to be spinning, not a galaxy spinning. Galaxies do that, the entire filament. Nearly 300 galaxies, 50 million light years of connected structure, rotating as one coherent system at roughly 110 kilometers per second. That's not supposed to happen, or at least nobody had directly caught it happening before. And what it implies about how galaxies get their spin, how dark matter distributes itself, and whether the cosmic web is actually alive with organized motion that changes how we think about the architecture of everything. So let me walk through what the Oxford team actually did, because the method matters as much as the result. The study was co-led by Dr. Lila Jung and Dr. Madalena Tudorage. They used data from MeerKAT, that's one of MeerKAT's flagship deep sky surveys, combined with optical observations from the Dark Energy Spectroscopic Instrument and the Sloan Digital Sky Survey. MeerKAT itself is an array of 64 interlinked radio dishes sitting in the Karoo region of South Africa, and it's particularly good at one thing: detecting the 21 centimeter emission line of neutral hydrogen gas inside galaxies. Why hydrogen? Because hydrogen is the raw fuel for star formation. Where you find hydrogen-rich galaxies, you find systems that are still actively growing, still pulling in material from their surroundings. And critically, hydrogen emissions let you measure Doppler shifts. With extreme precision, you can tell which galaxies are moving toward us and which are receding, even across enormous distances. Inside a much larger filament containing over 280 galaxies spread along roughly 50 million light years of space, the team isolated a narrower substructure, 14 hydrogen-rich galaxies arranged in what they described as a razor-thin chain, about 5.5 million light years long and only 117,000 light years wide. To put that in perspective, the chain is nearly 50 times longer than it is thick. It's essentially a cosmic needle. When they mapped the velocities of these galaxies relative to the filament's central spine, a striking pattern appeared. Galaxies on one side of the spine were systematically blue-shifted, moving toward us. Galaxies on the opposite side were red-shifted, moving away. That velocity gradient is exactly what you'd expect from a structure rotating around a central axis, like a slow-motion barber pole made of galaxies. But the surprises didn't stop there. Many of the individual galaxies within the chain were also spinning on their own axes, and their internal rotation axes were aligned with the filament's overall rotation direction. Tudorage described the filament as a fossil record of cosmic flows, a snapshot of how matter and angular momentum have been channeled through this corridor over billions of years. Jung, for her part, compared the whole setup to a teacup ride at a theme park. Each galaxy spins like a teacup on its own platform, but the entire platform is the filament is also turning. 2 levels of coordinated rotation nested inside each other on a scale that dwarfs anything astronomers had resolved individually before. Now, I need to be clear about why this is such a significant result, because if you're not steeped in cosmology, it might sound like, okay, big thing spins, cool, But the reason astrophysicists have been paying close attention to this paper is that filament rotation on this scale challenges a fairly foundational assumption about how galaxies acquire spin in the first place. The standard framework is called tidal torque theory. The basic idea is this. In the early universe, matter wasn't distributed perfectly evenly. Small density fluctuations meant that as regions of matter collapsed under gravity, the gravitational pull from neighboring structures wasn't symmetrical. Those asymmetric tugs created torques, rotational forces that set collapsing gas and dark matter spinning. Over hundreds of millions of years, that spin got locked into the structures that became galaxies. Under this model, cosmic filaments are treated as essentially passive infrastructure. They're the highways that deliver gas to galaxies and funnel matter toward the dense clusters sitting at the intersections of the web. Filaments shape where things go, but they're not usually credited with actively spinning or transferring angular momentum to the galaxies embedded inside them. This Oxford result flips that assumption on its head. If the filament is rotating, and if the galaxies inside it have their spin axes aligned with that rotation, then those galaxies didn't develop their angular momentum independently through local gravitational interactions alone. They inherited some of it, and possibly a lot of it, from the large-scale motion of the filament itself. That's a fundamentally different picture of galaxy formation. It means the cosmic web isn't just a skeleton. It's a dynamic system that actively shapes the rotation properties of the galaxies living inside it. And this isn't completely out of nowhere. In 2021, Peng Wang at the Leibniz Institute for Astrophysics, Potsdam, along with Noam Libeskind and collaborators in China and Estonia, published a paper in Nature Astronomy showing statistical evidence of filament rotation. They stacked data from thousands of filaments in the Sloan Digital Sky Survey and found velocity patterns consistent with spinning. But that was a statistical signal averaged across many filaments. Nobody had caught a single, well-resolved filament doing it in real time. That's what makes the December 2025 result different. This isn't an averaged signal. It's one filament mapped galaxy by galaxy, with both individual spin alignment and bulk rotation confirmed in the same system. As Wang himself commented, detecting this kind of coherent motion in a single structure is exceptional because the signal is faint and requires extremely careful data collection. Now, I know some of you are thinking, okay, a big structure rotates. Galaxies rotate, the solar system rotates, everything rotates. Why does this one filament matter so much? Here's the part that I think gets underreported every time this study comes up. This isn't just a discovery about motion. It's potentially a new measurement tool for dark matter. Filaments are not mostly made of galaxies. Galaxies are the visible minority. The bulk of a filament's mass is dark matter, the invisible gravitational scaffolding that holds everything together. We know dark matter is there because galaxies rotate faster than their visible mass can account for. That discrepancy, measured through galaxy rotation curves, has been one of the strongest pieces of evidence for dark matter since Vera Rubin's work in the 1970s. But rotation curves only tell you about dark matter inside individual galaxy halos. They don't tell you much about how dark matter behaves on the enormous scales between galaxies, out in the filaments and voids of the cosmic web. That's a blind spot. Now imagine you can measure the rotation of an entire filament. If you know the rotation speed, 110 kilometers per second in this case, and you can model the density profile of the filament's core, you can start estimating how much total mass is required to sustain that rotation. And since most of that mass is dark, you've got a new, independent method for probing dark matter distribution on scales of tens of millions of light years. Noam Libeskind, who co-authored the 2021 statistical study, has been arguing for years that filament dynamics could eventually let us weigh the dark matter content of the cosmic web. This Oxford finding hands him and anyone working in that direction a concrete, observable case to test against. So this is not an abstract exercise in cosmological aesthetics. If we can find more rotating filaments and measure their dynamics precisely enough, we gain a tool that lets us map dark matter distribution on the largest connected scales in the universe. That's a capability we don't currently have. So the obvious question is, how common is this? Is this filament an outlier, like some cosmic freak? Or is, rotation a general feature of the cosmic web that we've simply been too blind to detect until now? The honest answer is we don't know yet. Jung herself has said that statistically, there are likely other spinning structures out there, some potentially even larger, but current instruments and data sets haven't been able to resolve them individually. The MeerKAT survey that made this detection covers a relatively small patch of sky. Scaling that approach up to the full observable universe requires next-generation hardware, and that hardware is coming. The Square Kilometre Array, the SKA, is under construction in South Africa and Australia right now. When it comes online, it will survey neutral hydrogen across volumes of space that make MeerKAT's coverage look like a postage stamp. Tutor H has said directly that the SKA should allow researchers to identify more of these individual rotating filaments, moving the field from anecdote to statistics. On the optical side, the Vera C. Rubin Observatory in Chile is preparing for its legacy survey of space and time, a 10-year campaign that will photograph the entire visible southern sky every few nights. That's going to give us deep, repeated imaging of galaxy alignments and structures that can be cross-referenced with hydrogen maps from radio telescopes. The European Space Agency's Euclid mission, already in orbit, will add infrared and visible light surveys designed specifically to map the distribution of dark matter and dark energy across cosmic time. The convergence of these instruments matters because no single telescope can answer the question alone. You need radio data for hydrogen dynamics. You need optical data for galaxy positions and alignments. You need wide field surveys for statistical samples and deep field surveys for individual resolution. For the first time in observational astronomy, all of those capabilities are arriving within the same decade. The questions this opens up are specific and testable. Do galaxies inside rotating filaments evolve differently from those in non-rotating filaments? Does filament rotation depend on the age of the filament or its position in the cosmic web? Can rotation speed be used as a reliable proxy for dark matter content? These aren't speculative, they're hypotheses you can design surveys around. And if the answer to even one of those turns out to be yes, it rewrites portions of the galaxy formation models that have been standard for decades. And here's where I'll plant a flag. I think within the next 3 to 4 years, once the SKA's early science operations overlap with Rubin's first data releases, we're going to see at least a half dozen more individually resolved rotating filaments published in the literature. And I think at least one of them will be substantially larger than this one. If that happens, filament rotation stops being a curiosity and becomes a diagnostic tool. It becomes something cosmological simulations have to reproduce to be considered credible. And it means the cosmic web, this structure we've been mapping for decades, as if it were frozen scaffolding, is actually churning, twisting, and feeding angular momentum into galaxies in ways we're only now beginning to measure. The universe isn't just structured, it's in motion, and we finally have the instruments to prove it.